All right, so today we're going to be talking about the ratio test. Now, the ratio test, just like any other test, is going to be a tool in our toolkit that we're going to be able to use whenever we're given a series problem and we're asked to find its convergence or divergence. So, let's start off with a simple series, summation n is 1 to infinity of a to the n. Now, we know that knowing the limit as n approaches infinity of a to the n equals 0 is not sufficient in determining the conditions for convergence. What we would need to know is that the limit goes to 0 and that the limit goes to 0 quickly enough, okay? So we need to know that the terms in the series are going to get smaller and smaller fast enough so that its sum of that series is going to be convergent, right? It's going to be a finite number as opposed to drifting off to infinity. So we're going to look at two cases that are going to illustrate this problem pretty well. So the first is going to be the summation from 1 to infinity of 1 over n, and then the other is going to be summation from n is 1 to infinity of 1 over n squared. Now we know the first case, 1 over n, is the divergent harmonic series. But the second case, 1 over n squared, is a convergent p-series. Now, why could these two functions, which look pretty close together, or I should say two series that look pretty similar, how is it that one diverges and one converges? Well, it has to do with how quickly the term a to the n is approaching 0, right? Just like we talked about. 1 over n approaches 0 quite slowly, whereas 1 over n squared, since we have the n term squared, it'll grow faster than the denominator, which means the whole term is going to approach 0 more quickly. Okay? So this leads us to the ratio test, right? We want to be able to determine how fast terms of a series are going to approach 0. The ratio test is going to provide a perfect and nice and neat way of measuring how fast those terms of a series are going to approach 0. So let's take a look at the ratio test in its full. So let's take our series n is 1 to infinity of a to the n, and we're going to set up a new limit, L, which is equal to limit n approaches infinity, absolute value a to the n plus 1 over a to the n. So we're taking the next term and we're dividing by the previous term, and then we're going to take the limit as n approaches infinity of that absolute value. So what this means is that if the next term, a to the n plus 1, is bigger than the previous term, a to the n, this ratio is going to be bigger than 1, and so the limit is going to be bigger than 1. Now this is going to prove to be a divergent series in that case, right? Because if the next term is larger than the previous term, and you're starting to add these values together, your series is going to go off to infinity because you're adding larger numbers than what you previously had. What if the two are equal, right? What if a to the n plus 1 a to the n, the next term and the previous term, are the same? Well, then our test is inconclusive, right? We're not seeing any change in the values, right? We don't know if the values are getting bigger, if they're getting smaller. They're staying basically stagnant, which means we can't tell if we're going to converge or diverge. We're going to say we're inconclusive if my limit is equal to 1. If the limit is between 0 and 1, however, we're going to say that the series is going to converge absolutely. And the reason for this is because when when the limit itself is going to be between 0 and 1, that means that the next term, a to the n plus 1, is actually smaller than the previous term, a to the n, which is what we would hope for, right? We need the values to get smaller and smaller and smaller, so when you sum them up, we're going to hopefully converge to a finite number. So this is the rule. We're going to take the limit, we're going to plug in the next term, divide by the previous term, put in absolute values, and we're going to figure out what that limit is equal to. And we'll use these conditions to determine whether we're divergent, convergent, or if we're inconclusive for that test, and we'll have to apply some other test. So this leaves us with a question, when should I use the ratio test, right? When to use the ratio test? Well, the ratio test is going to prove useful in two cases. So particularly when we have factorials and when we have exponentials. And the reason that these two are such great functions to use the ratio test with is because that the ratio of their terms are going to simplify so well. So remember, we are doing a division of the next term divided by the previous term. So when you work with factorials or you work with exponentials, they tend to cancel out nicely when you just add 1 to them, okay? We're going to do a quick example just to illustrate this property. So let's take the summation from n is 1 to infinity of 2 to the n over n factorial. Now remember, using the ratio test, what we're going to see is L equals the limit as n approaches infinity of 2 to the n plus 1. Remember, this is the a to the n plus 1 term, n plus 1 factorial, and we're going to divide it by the original a to the n. Right? So like I said, this here is a to the n plus 1. This here is a to the n. And what we're going to do is we're going to simplify this. Now, generally, as we get better at this, we'd probably write it at the first step like this. So remember, we can do a keep change flip when we have this complex fraction, and we can simply write it as that. And this is going to simplify nice, where we see 2n plus 1 over 2n. What is that going to give us? Well, it's just going to give me a 2 in the numerator. N factorial over n plus 1 factorial, that's going to result in just an n plus 1 in my denominator after we've simplified. And you can take the limit as n goes to infinity. So what is the limit of 2 over n plus 1? Well, it would be 2 over infinity, which is 0. And according to our ratio test, so remember coming back up here, the ratio test claims that if I get 0, that I'm going to have an absolutely convergent series. So what this means is that my original series, which is 2dn over n factorial from 1 to infinity, is absolutely convergent. And there we go. That's the ratio test in a nutshell.